Now that we have defined the definite integral of a function over a closed interval, we're going to go through a few examples. Just to remind you the way we've defined the definite integral in the previous video, we take a pointed partition of the interval AB on which we integrate the function, and then we define the Riemann sum for the function and the partition this way, as the sum from 1 to n, where n is the number of subintervals in the partition, of the product of the value of the function f at the sample point multiplied by the width of the interval, and we do that for each subinterval, and sum up what we obtain. And the integral of the function on AB, if it exists, is the limit of these Riemann sums as the parameter of the partition goes to 0, where this parameter is by definition the maximal width of the subintervals. And in the case where this limit exists, the notation we use for the integral is this integral from a to b of f of x dx, where this elongated s stands for integral. And what we have seen is that this integral exists as long as the function is continuous on the interval, and that in the case of a continuous positive function, this integral is in fact the area under the graph of the function over the interval. Now, what if the function is not positive on the interval AB? In other words, it changes sign, potentially. So like in this case, the function changes sign on AB. Remember that the integral is the limit of the Riemann sums as a parameter of the partition, pointed partition, goes to 0. So if we look at a particular pointed partition and the corresponding Riemann sum, it is expressed by this formula that we have at the bottom. And if I look at a particular subinterval that is, for instance, in this part, corresponding to a part of the graph of f where the function is positive, then you see that this term f of xk star, the value of the function at the sample point, times the width of the subinterval, correspond to the area of this rectangle. On the other hand, if I'm looking at one of the subintervals in the pointed partition that is in a part of the x-axis over which the function is negative, then you see that the corresponding term in the Riemann sum, f of xk star times the width of the subinterval, now is the opposite of the area of the rectangle, because f of xk star is negative. And so in this Riemann sum, the contribution corresponding to parts that are where the function f is positive is going to correspond to an approximation of the area between the graph of f and the x-axis, while for the parts where the function is negative, it's going to correspond to the opposite of the area between the x-axis and the graph of f. So in particular, for this blue part, the subintervals that correspond to this blue part, the sum in the Riemann sum of the f of xk star delta xk for these particular intervals is going to approximate the opposite of this blue area. As a result, when we go to the limit, what we're going to obtain is that the geometric interpretation of the integral from a to b of the function is the sine sum of the areas between the graph of the function and the x-axis, where the areas that are above the x-axis are counted positively, in our case a1 and a2 in red, or areas enclosed between the graph of the function and the x-axis where the function is positive, so these areas that are above the x-axis are counted positively. I get a1 plus a2, and then I subtract the area that is enclosed between the graph and the x-axis but is below the x-axis. I get this a1 plus a2 minus a3. Okay, now let's turn to some examples. Let's say we want to evaluate the integral from 0 to 1 of the function square root of 1 minus x squared. It is not something that we would like to do, to start writing Riemann sums for this and try to understand the limit behavior of these Riemann sums. This looks like something complicated. Remember that it was already quite complicated for a much simpler function, just the square function on 0, 1. So let's try to see if we can have some insight with geometric interpretation. If I draw the graph of this function, here is what I get. And because the function is positive, the integral from 0 to 1 of this function is the area under the graph over the interval 0, 1, so this red area. The graph of the function looks like upper half circle. If indeed it is a circle, when I take the reflection about the x-axis, I would get the full circle. If I draw the opposite function, which would give me this reflection, here is what I obtain, and indeed it really looks like a circle. And indeed it is, because if you look at the equation of the circle centered at the origin and of radius 1, which is what we have on this picture, it's x squared plus y squared equal 1. And so when you solve for y, you get plus or minus square root of 1 minus x squared, where of course the choice of plus square root of 1 minus x squared corresponds to the upper half circle, and minus square root of 1 minus x squared corresponds to the lower half circle. As a result, now we can calculate our integral, because now the red area is 1/4 of the area of the disk of radius 1, and the disk of radius 1 has area pi times 1 squared. So what we obtain is 1/4 of pi times 1 squared, so pi over 4. Turning to a different kind of function, I'm looking at the integral from 0 to 3 of x minus 1. If we draw the graph of this function, that is what we get. Now going back to the geometric interpretation of integrals that we have seen, this integral should be obtained by looking at the area between the graph of the function, this straight line, and the x-axis, and count positively the area that is above the x-axis and negatively the area that is below. So here, the graph is below the x-axis, so this blue area is going to be counted negatively, while this red area above the x-axis is going to be counted positively. The blue triangle here has base 1 and height 1, and therefore its area is base times height over 2, so just 1/2. Similarly, the red triangle has base of length 2, height of length 2, and therefore it has area 2 times 2 over 2, in other words, just 2. That means that my integral is the red area, which is 2, minus the blue area, which is 1/2, so I obtain 3/2 for the integral from 0 to 3 of x minus 1. What about something a little bit more abstract, where we look at the integral from a to b of x dx, where we don't really know what a and b are? So here is a graph of y equal x, and for the sake of argument, we're going to take a and b both positive with b greater than a. We're going to obtain a certain formula for this configuration, and I'm going to use a geometric argument. I encourage you to look at what happens if you place a and b in different positions. You will see that we would obtain the same formula, but I'm not going to go over all the possible configurations for a and b. So in our case, we assume that a and b are positive and b is greater than a, and then x is a positive function on that side, right, on the positive x-axis, and therefore the integral represents the area under the graph, therefore this red area. Now you see that because the equation of the line is y equal x, we have these points of intersection with the graph y equal x that have coordinates AA and BB. So that means that we can calculate areas covering this red area by, for instance, looking at this rectangle that has one side of length b minus a and the other one of length a. Therefore, its area is a multiplied by b minus a. And then the remaining triangle is half of this square, which is a square of side b minus a. So that means that the triangle has area b minus a squared over 2. So this is what we obtain for the integral from a to b of x dx. It's a times b minus a plus b minus a squared over 2. If we multiply things through in the first term, we get ab minus a squared. And if we put everything over 2, then the first parenthesis gives me 2ab minus 2a squared. And if I expand the square, I get b squared plus a squared minus 2ab. Simplifying this, you see that the two ab's cancel out, and then I have b squared plus a squared minus 2a squared, so I end up with b squared minus a squared over 2. So this is my formula, and as I said before, I have established it with a geometric argument in this particular configuration. I encourage you to play around with other configuration and convince yourself that you would have exactly the same formula. Now turn to the next video to look into properties of the definite integral.